tentative plan for today is to revisit the expectation values of spin projections, recall the solution for wave function, maybe for the last time before we go to density matrix, and make an attempt to combine these two things and use them for introducing an exploration of block sphere. Those of us who have practiced yesterday lab already did it numerically, but we can do it in the analytical form. And then when we were finishing Tuesday lecture, we did about 25% of the equation of motion for density matrix. We will return to it, and I hope it will be about amount of information before break. And then the plan for the rest of the meeting, we will try to repeat this analysis of block sphere in terms of the density matrix, and it is very possible and it is very comfortable. And if time allows, we may make our first step towards concept of ensemble average. Ground state 1, excited state 2, two-level system, energy 1, energy 2, and the external electromagnetic radiation of frequency omega. So the omega and atomic transition are offset by the value delta E or simply delta detuning. So the Hamiltonian of interaction is dipole strength electric field cosine frequency. So know that here is the frequency of electric field, and it doesn't have any label, so cosine omega t. And if we have the full Hamiltonian in it will be just Hamiltonian in the rotating frame in the matrix form. We will, if we do it carefully and include non-zero detuning, then we will have the
Sorry, Dr. Killing, I just want to confirm, are you writing on the board?
Yes, I'm writing on the board.
Okay.
So, yeah, thank you, Patricia, for asking. Do you see the board? Is it transmitted to the to what you see? Or so I'm writing in the very bottom.
I've been seeing where you're writing.
So it's bottom left part of the board, right?
Yeah.
Let me, I'm going to zoom out and zoom in so that everyone does see it, and there will be no confusion.
Okay.
I took what we did together as a group yesterday and just went a little bit to the left, because the your introduction that was done collectively for expectation values of spin projections can be used today during the meeting. So we may want to admit annotation that the electric field amplitude times transition dipole over Planck constant will be defined as Rabi frequency. The energy offset. Okay, energy offset between energy levels is delta E, and offset between excitation frequency and the transition will be delta without epsilon. So simple delta. Okay, we have notations. Then right now we are not going to solve, but our exercises in the past and your experience would be sufficient to prove that it can be done in another 15 minutes of derivation, that in absence of the detuning, if the excitation light is in the resonance with the transition, the solution for the expansion coefficients of C1 and C2 as function of t can be expressed as a sine Rabi frequency t divided by 2 and I sine Rabi frequency divided by 2 times t. In case we do have the detuning, non-zero detuning, this solution will be slightly modified. So with non-zero detuning, C1 will be the same thing as before, a sine omega Rabi time over 2, and it will be accumulation of phase e to the power plus I over h bar delta over 2 t, and for upper level sine omega Rabi t e minus I over h bar delta over 2t. So we are going to explore how this solution for wave function for expansion coefficients would affect 3 observables. So basically we will do by hand, by pen and paper, the effort that was made yesterday by the computer code, with the only thing that we probably will not model the train of pulses, we just do continuous excitation. So to work with this solution for wave function and plug it into definition for expectation values of spin projections, we may want to shorten notation so that we make our effort as quick as possible. So there is a suggestion to denote this Rabi frequency times over 2 as theta, and it deals and relates to pulse area theorem, and the phase accumulation happening here can be, one can try to catch it into the angle phi. So it changes nothing for this solution, but it creates a shorthand notation. So for the next stage, I'm going to borrow the achievement of the class of all attendees that was done yesterday. So, and please correct me if I'm wrong. I probably can just look into different area of this board. So if we need SZ, we have H bar over 2, C2 star C2 minus C1 star C1. If we do need SX, we do have I would miss what goes first, what goes second, probably C2 star C1 plus, or if they're symmetric, it doesn't matter who goes first. C2 C1 star, and if one needs SY, there should be H bar 2I, C2 star C1 minus C1 star C2. So if you see errors, please correct, and I will be happy to record credit from time to time to those who find errors. It's just needed to have a healthy progress. Okay, so what we are going to do is to just plug in the solutions from here to there and see what happens. So it will be not a big wonder, but we better do it carefully and get some results, so that later on, when we jump into a little bit more advanced techniques, we see immediate connections. So SZ will be √2. So C2 minus plus I minus I sine square of theta, and then we do have e to the power plus I phi, e to the power minus I phi. So the complex parts cancel, minus the C1 parts do not have imaginary parts, so it will be just cosine squared theta, and the imaginary exponentials just evolve in the opposite directions, but they still cancel, minus I phi plus I phi, and they both can be cancelled. H bar over 2 sine squared theta minus cosine squared theta. Does anyone remember any equations from high school about trigonometry? can one simplify this subtraction of sine squared and cosine squared? Do not hesitate to write directly if you have some hypothesis. We are in a very relaxed democratic environment.
We could turn it into like 1 minus 2 cosine squared, if that helps.
Okay, can we convert it into cosine of double argument?
That sounds about
Yes.
right.
So how would it look like?
There would be negative cosine 2 theta.
Negative cosine 2 theta. Okay. Let's. I wouldn't correct it from the top of the head, but let's keep it for later check. But I like the idea that we go into double argument. So it will fix that the fact that by change of the angle theta, we go through the whole Rabi cycle twice as quickly. So it relates to a question by Patricia from yesterday. Minus, let's think about minus. If theta is 0, if you didn't start dynamics, we start in the ground state, so the vector block vector directs to the south pole, so it should be negative. So Adam +1. Thank you. Thank you, Adam. Okay. Let's continue for other parts of this game. So SX. It starts to decline in effort. Okay, so H bar O2. And then we do need to put the plus I sine theta. And then for C1, we are getting cosine theta. And then from C2, you get exponential accumulating in the plus I or H bar delta O2. Oh, we agreed to follow the notation of phi. So and from C1, it will be also plus, so it will accumulate the phase in the same direction. Okay, the second term. So from C2 without star, we get minus I sine theta. From the C1 with star, we get cosine theta. And then the imaginary part from C2 will be E to the power minus I phi. And from C1 star, it will be E again minus I phi. So unlike the SZ projection, we do have the imaginary parts do not cancel. So we have H bar I 2 sine theta cosine theta can go outside of the brackets. And inside brackets, we do have e to the power 2 I phi plus e minus 2 I phi. At the end of this exercise, I'll check with the cheat sheet. I think the imaginary unit shouldn't be here, but right now I do not see where the error. So the sine theta times cosine theta is 2 sine of theta times cosine theta will be sine of double argument, sine of 2 theta. Please confirm if we got this in the high school trigonometry, right?
Looks right.
Okay, thank you. No one objects. And the combination of two exponentials, imaginary exponentials going into the opposite direction will be 2 cosine of 2 pi. So we have 2 h bar I, and this I is my error. It shouldn't be here. We'll fix it later. I'll find where it comes from. So cosine, not cosine, sine double theta times cosine double phi. Okay, there is an error, but let's go forward, and I hope to fix it soon. So, and the third one, the SY. And I believe we just reproduce the same terms as for Sx, as in the previous line, but with the opposite sign between these terms. So we're getting I here. Then we can put two sign one half sign of double argument, sign double theta, and then another bracket where we would have e to the power pi minus e minus 2i phi. So the factor 2i in the denominator would make it sine of 2i phi. And then we are getting h bar I. I'm also not sure about this factor 1/2 sine 2 theta sine 2 phi. So somewhere in the definitions, I did a mistake with imaginary unit. So in the cheat sheet, the imaginary unit was not there. So if anyone has an idea where it came from, it will be appreciated. So this imaginary unit is not needed. H bar over 2 is correct, and this part is correct. Here should be H bar over 2, and imaginary unit shouldn't be there. Something was an error on my side, and the rest is correct. So the Sx projection and Sy projection both are coming out, if things are done correctly, to be real, and they have the same factor originating from transitions between ground and excited. So sine double theta is present in both expressions, but they are different by cosine 2 phi and sine 2 phi. So as z is h bar over 2 negative cosine 2 theta, agree, and then the Sx Sy do have these expressions. So as long as we have completed these expressions, we may attempt to represent three projections of Sx, Sy, Sz as a vector in three-dimensional Cartesian space. And we do have a understanding that angle theta increases when system is experiencing transitions driven by external field, and angle phi is changing linearly, also changing linearly in time if the detuning is larger than 0. So one needs to draw 3 coordinates: Sx, Sy, Z. Sx, Sy, Z, and then the quantum state of two-level system is expressed as a point in three-dimensional space. Vector of pseudospin is average expectation value of pseudospin is composed of 3 projections. So let's analyze what it is and try to create a visual interpretation. So before we go to three-dimensional image, let's assume that Rabi frequency is equal to 0, close to 0, and we do have only dynamics of increasing the angle phi. So then it will be a projection onto the plane Sx and Sy. And Sx will behave as cosine phi, as Y will behave as sine phi. So when angle is 0, we start only at the x-axis, and as angle phi increases, we will go for cosine projection getting smaller and sine projection increasing. If I do not have minus sign, then it should go into the opposite direction. Let me fix it. As we do have in the equations here, it goes to the. I want to make sure that I didn't made an error.
I found where that I should be going away, by the way.
Okay.
So this should be 2 cosh
if I
of I.
showing right place. So you are checking it here?
Up in here.
Okay.
So the exponentials would give you 2 times a hyperbolic cosine within imaginary argument. And then if you have an imaginary argument in a hyperbolic trig function, you can just pull that out and put it in front of a regular trig function. So then this would be equal to 2i regular cosine of 2 phi.
Okay. Yeah.
And then this I and that I will cancel each other.
Okay. Thank you, Landon. It's a good hypothesis. It brings to a correct answer. But I want to double check over again because as of now, summation of 2 oscillating exponentials should give a regular cosine. So this imaginary unit right here shouldn't be here in the first place. So maybe I did corrupt the input data for the solution for the C1 and C2. But if I discover it before next lecture, I'll report. But thank you. I would be happy if your suggestion is correct and it positively brings us to correct answer. Okay, so right here, as cosine 2 phi increases, x projection decreases. As sine 2 phi, s 2 phi increases, sine increases. So I was doing it in the right direction. So we are going counterclockwise. And at some point, sx projection is 0, sy is maximal, and then we continue the circle. So since the sx and sy are projections of cosine 2 phi and sine 2 phi, it is just an equation of circle with radius 1 that goes around. So if we import this image and project it onto our three-dimensional representation, it will mean that in case there is an absence of electric oscillating electromagnetic field, original position, original vector for representing state of two-level system in three-dimensional Cartesian projection would keep projection on the SZ constant and perform oscillations in the conjugated way in the plane of Sx and Sy. In case initial, so basically precession, in case of initial vector will be like 50-50 between Sz will be 0, it will be a little bit bigger radius, and it will perform this equatorial motion. If initial vector would be not absolutely negative, but some angle down to the negative hemisphere, south hemisphere, then it will be a circle counterclockwise in there. So by now we do not have a proof that the vector must have the same length all the time. We are going to prove it in the next step. But this image, let's just assume that we will prove it in the future. The length of the vector specifying state of two-level system in the three-dimensional state is constant. So length of the S square, which is radius, is constant. And if we admit this statement, then any motion, any change of the state of the two-level system would correspond to a surface of a sphere. So all these trajectories were drawn on a surface of a sphere. And let me maybe artistically redraw it. So if we do a sphere, yeah, I'm not a good artist. It looks more like a potato rather than a sphere. So sphere, maybe add a little shadows. And then we do set up system of coordinates, like pinching potato or apple with the, I don't know, nails. X. Then we do have the third axis SY. Then in case we do not irradiate the system with external electromagnetic radiation, the time evolution of a system would correspond to a traveler performing trajectories parallel to equatorial line. It will be motion from west to the east and making it trying to encircle this little globe around. Now, what would happen if we have zero detuning, delta equals 0, and then we are not fixed with SX or SZ projection. We would stand at such angle phi where we got with initial conditions from origin, and then from there, from initial conditions, one would perform motion between circles between north and south poles, but this motion is not necessarily in the either SX as Z plane nor SY SX plane. It will be some direction between X and Y and SZ. And which plane will be selected for this vertical motion depends on initial conditions. So let me check the plans and time for the break. Okay, yeah, before we go to the break, I want to continue and introduce the equation of motion for density matrix. Yeah, I'll try to do it in 8 minutes. So we did started yesterday, and no, we did started on Tuesday, and we did define the 4 elements of density matrix for 2x2 systems. So is elements with coinciding indices and indices with and elements with different indices, and we define them as C star 1 C1, C2 star C2, C 1 star C1 C2 star and C2 C1 star. So we used we did have the equation of motion for both wave function that progresses forward in time and wave function coefficient that progresses backwards in time. So the C1 dot without star was I h bar delta over 2 C1, which corresponds to accumulation of phase minus I over 2 Rabi frequency C2, which corresponds to leaking of the probability amplitude between first and second state. The C2 is accumulating phase in the opposite direction minus I over h bar delta over 2 C2 minus I over 2, and here it is omega Rabi C1. If we do need propagation of the wave function backwards in time, which corresponds to just conjugated instead of so C dot 1 star, it will be absolutely the same equation with the only difference that any imaginary unit would get the change of the sign. So here we had plus, now we'll have minus. H bar dot over 2 C1. Here we had minus, now we will have plus I over 2 omega Rabi C2, and it is star and star. So we just recast Schrödinger equation. Here we expressed everything for the cat. Here we express everything for the bra. And for bra vector, it's not only row instead of column. It's also Hermitian the complex conjugation can be interpreted that we have regular wave function, but time goes in the opposite direction. And this interpretation is always often helpful in interpreting some calculations. So C dot 2 star. We had minus here, now we will have plus I over h bar delta over 2 C2 star. So if we flip time, it accumulates phase in the opposite direction, basically spin and unspin coil then here we have minus, so here we will have plus I with 2 omega Rabi C1 star. And what I'm going to do right now is to apply time derivative to the definition of elements of density matrix. putting dots will be a little quicker. DVT. And plug practice the derivative of a product, and then use either one of these four definitions to open the brackets. As a result, as a result, we will find such combinations of this expansion coefficients in their products, so that resulting expression will be reproducing definitions of one or another elements of density matrix. So as a result of this exercise, I'm going to obtain a set of linear differential equations where a derivative of each element of density matrix immediately results in a linear combination of the same or other elements of density matrix with certain coefficients. And my goal is to find and reproduce these coefficients. So I think it is 3 p.m. So if anyone needs a break, please go ahead and take a little relaxation for a few minutes. And I will start this derivation, but maybe without speaking too much, because it's more technical effort, and the comments I needed at a time when this field is filled with equations. So feel free to step out, relax, stretch, and I'll start commenting what is going on in a few minutes. Okay, should I continue the comments? At least no one objects. So if anyone has the energy and attitude, feel free to copy paste, or maybe we can do it as a collective effort, either by rewriting, or maybe, I do not know yet full functionality of this technology. Maybe one can practice the copy pasting these segments to save time. So like this segment should go there. This segment should go there. And similar protocol should be practiced for rest of lines. So it is a long effort, and maybe I'm not. It's my job to do it. But if anyone has energy to do derivations, maybe you can start from the bottom line and or like line number 4, line number 3, line number 2, And when I arrive to it, if something will be written there, I don't mind, and we'll find way to create it. Okay. So
Dr. Pilling, just to confirm, the C is like a function of time, right?
yes, yes, Patricia, thank you very much. C is expansion coefficient, and it does depend on time. A period on the top of C is equivalent to time derivative. So C dot is equivalent to ddt of C1. It just saves time in notations. And we assume that our wave function of this two-level system is composed as C1, state 1, ground, plus C2, 2, excited state. Does it make sense?
Yes, thank you.
Thank you. Oh, was it copy pasted? Who did this copy paste? Please teach me how to do it.
I did. So if you, on the toolbar on the side, if you just go to like a normal mouse, you can highlight sections of text.
Okay.
And you could just drag it to where you want it and resize.
Okay, that's really great. It saves a lot of time and effort. Let me. I'm not very skilled. It will be a little practice for me, but let's try. No. Undo. Try once again. When I'm trying to do, I'm catching more than I need.
I've been dragging it off into a different section and then just erasing what is not needed.
Okay. Try once again.
Just as a check, is the delta symbol in these expressions referring to like a time interval step or a energy level difference?
Delta stands for energy difference.
Okay.
So it is referred to as detuning, and it corresponds to difference between transition energy of the molecule and excitation frequency of the light.
Okay, thanks.
Oh, the one that I selected is not needed anymore. Okay, at least I was able to. Okay. Done. Special thanks, Tori, for explaining how to make copy paste and this idea of copying everything and then just erasing stuff that do not fit into. Even though for the first time, maybe writing directly would be, it take the same time, but after a little learning period, it definitely would give a great speed up. So we have only one left, which would be the time derivative of the first expansion coefficient moving forward in the opposite direction. C1. Yes, yeah. Thank you, Tori. I really enjoy this collective effort. It is so much better than being alone and writing personally. Thank you for it's really great collective effort. I enjoy it so much. Okay, so let's try to identify what do we get. So if one doesn't think and just blindly converts everything what is obtained, then in each line we should get 4 terms. So in the first line, I will get minus I h bar delta over 2 C1 star C1. Then second term will be plus I over 2 Rabi frequency C2 star C1. Then the term number 3 will be plus I over h bar delta over 2 C1 star C1 minus I over 2 Rabi frequency C1 star C2. So now one would need to identify the definitions. So C1 star C1 was defined as rho 1 1. The third term again is C1 star C1. It is also defined as rho 1 1. One can observe that they do have opposite signs if the derivative was taken correctly. So first and third terms are cancelled. Now let's continue identifying C2 star. C1 is defined as row 1, 2. Row 1, 2. C1 star C2 is defined as row 2, 1. Row 2, 1. So the terms that contain off-diagonal terms of density matrix both have factors of Rabi frequency, but they are coming with opposite signs. So let's say it is I/2 Rabi frequency, and then subtraction of row 1, 2 minus row 2, 1. And to summarize it, so it will be the time derivative of row 1, 1. So in the first line that I have completed, I did found that time derivative of the diagonal element is equal to subtraction to linear combination of the off-diagonal elements, and is factored by Rabi frequency. So let me focus. Yeah, please keep writing it. It's a really great help. So now I'm looking on the purple writing by Tori. So she has also identified that there are two terms that are cancelled. And then there are off-diagonal terms row 1, 2 and row 2, 1. And when one is observing then I/2 Rabi frequency, 1, 2 minus 2, 1 will be row 2, 2. Okay. The thing before we complete this, I want to check the signs. So should it be the same sign here and there, or they can be different? So row. Let me double check and focus here. C1 star C2. C1 star C1 star C2 was defined as row 2, 1. So Tori, would you agree that as our definitions, this was defined as row 2, 1?
Yeah, my apologies. I was going in
okay.
order with.
That's okay. I might be wrong. Okay, and then another one would be row 1, 2, right? And then yeah, thank you much. So we have, so to say, confirmed equations for diagonal elements and we see that time evolution of the diagonal elements of density matrix is equal to the subtraction of diagonal elements. But for ground state and excited state, the sign is different. So here we have 1, 2, minus 2, 1. Here we have 2, 1, minus 1, 2. So it means the populations change in the opposite phase. Okay, let's see the third line. So row 1, 2, row 1, 1, row 1, 2, row 2, 2. So let's see if anything can be cancelled, or maybe not. So one, two. And here is row 1, 2 once again, right? Who is writing the third line?
Me.
Okay, yeah, thank you, Hadassah. So it looks like we do have row 1, 2 coming, if everything is done correctly, row 1, 2 is coming up 2 times.
Yeah, they're just add together.
Okay.
Wait, they don't have the same factors. Or they do. Never mind.
Okay. And then instead of delta over 2, it will be delta, right?
Yep.
I over h bar delta row 1, 2. Okay, very good. So and then there will be 2 more terms for row 1, 1 and row 2, 2. So they have a common factor I over h I over 2 Rabi frequency. And then we do have subtraction of row 1, 1 minus row 2, 2. Okay, so this is time derivative of row 1, 2, right? Please correct me if I'm wrong. Okay, so we do see that time evolution of the off-diagonal element consists of 2 elements. First, that off-diagonal element accumulates phase proportional to the detuning, and it accumulates phase in the like opposite direction, not with minus as usual, but with plus in the plus direction. So phase is withdrawn. So it's one factor, and another factor is that it gets increased in proportionally to the difference between populations of ground and excited state. So if there is a population inversion, then it promotes increase of the off-diagonal element. Okay, and I do see there are results for the line 4. I saw last expression was written by London, but I appreciate help of everyone. So the time evolution of the another off-diagonal element has a trend of similar, but with different things. So with 2, 1, it accumulates phase in the opposite direction compared to row 1, 2. So this one accumulates phase in the opposite direction as it is in a more normal direction, counterclockwise. And it gets increment in case populations of ground and excited are not equal. This is most perfect. This is most perfect. I really appreciate this collective effort. So yeah, and we are doing really great this time. Now I'm going to practice a little bit of calligraphy and rewriting this 4 equations of motions in the once again, but I do have a specific goal that I will pursue. And let me explain and play open cards before we go forward. So we always keep in mind doing something related to computation, because things beyond two-level system and harmonic oscillator will be, and maybe rotator and hydrogen atom will be not so solvable analytically. So right now, these 4 equations, you did a great job. I'm very happy. These equations can be characterized as a system of first-order linear differential equations, right? And although density matrix is a matrix 2 by 2, but the system of linear differential equations can be written as a column. So this 4 elements of density matrix are nothing but variable that one needs to solve in a system of linear differential equation. So I want to rewrite this equation that we collectively derived in a specific form that will be most comfortable for mathematical and computational processing. So I'm going to write down all 4 elements of density matrix as a column, as a one column instead of matrix. And just for symmetry, for some purposes that I will disclose later, I will write diagonal elements at the beginning and at the end here. 1 row to 2, and off diagonal in the middle. Row 1, 2, row 2, 1. So by mathematical liberty and freedom, no one forbids me to do so, right? I just store data in the comfortable way. Now, let's explore what would be the time derivative of this column vector. We do know from the equations that you have derived that it will be only linear combinations of the of the elements of density matrix without derivative in the first order. So we can write it down as column of elements of density matrix without derivative, row 1, 1, row 2, 2, row 1, 2, row 2, 1. And now I do have a symbolic matrix, which is nothing but an attempt to store coefficients that would govern the system of linear differential equations. So basically, I want to distribute coefficients from these equations that we collectively derived into this matrix. And if you can, you are very welcome to assist. So the convention, the rule that will be that by making row by column multiplication of this matrix by this column, we would reproduce 4 equations that have been just derived. So I'm looking how the time derivative of row 1 is contributed by this 4 elements. So the diagonal element doesn't contribute to time derivative of diagonal element, 0. Diagonal element row 2 also does not contribute to the evolution of diagonal element row 1. The of diagonal element 1, 2 contributes to the diagonal element row 1 as I over 2 omega rabi with plus sign. Element row 2, 1 contributes to the dynamics of diagonal element row 1, population row 1. So I took off the bracket, I'll put it back. With negative sign, so negative I over 2 omega rabi. I guess there will be another 0 here. So I'm following whoever does another diagonal element. So row 2 has, so when we do row, I'm following whoever is operating purple. Okay, so let's look how the element row 1, 2 contributes to the increment of the population row 2. So it comes with the negative sign, right? So I believe it is minus here. Please check and confirm. So right here in your derivation, row minus row 1, 1, 2 with this Rabi frequency contributes to row 2.
Yes, I missed that. My bad.
Okay, thank you. All good. I appreciate it. And then in this element, I think it should be Rabi frequency, imaginary unit, but with plus sign, right? Okay. Yeah. And now we see there is some sort of symmetry. For the in the top row we have minus here plus there, and in the bottom row we have minus in this column and plus in this one. So they kind of swapping. Okay, let's see what happens for row 1, 2. It hasn't been placed here. So for row 1, 2, the row 1, 2 itself contributes to its own derivative. Is plus I delta divided by H bar. So I'm looking on this yellow thing. Then the element row 2, 1 does not contribute to evolution of row 1, 2. So we put it 0. And then let's analyze these contributions. So the population row 1, 1 does contribute to the increment of coherence of diagonal element row 1, 2. So it will be here by plus I over 2 Rabi frequency. Then the population of the excited state contributes to coherence row 1, 2 with negative sign minus I over 2 omega Rabi. Okay, we are almost done. Let's check what is going on with the last. So increment of coherence to 1 is gaining from itself with a factor minus I over h bar delta. So gaining from itself, it means on the diagonal of this supermatrix. So we put minus I over h bar delta. Now, the gain of the coherence rho to 1 yields from population of the ground state with minus I over 2 Rabi frequency. Yes. And we have the last element here. So it is how the coherence rho to 1 gains from population to 2. So it gains with a positive sign plus I over 2 Rabi frequency. So I congratulate everyone on completing this important accomplishment. So as of now, we are yet in the reversible Hamiltonian evolution of the two-level system, but we do have performed transition from Hamilton space to Liouville space. If any of you was looking onto the book by Shaul Mukamel, and if anyone is interested, I can just bring it into class, or we can find a way to share. So he makes main point of his book is redoing all quantum mechanics in the Liouville space. So we got this matrix 4x4 and 4 independent coefficients by processing the matrix of 2 elements d dt. So we used to have matrix 2 by 2 for linear differential equation of for expansion coefficients of the density matrix, and the original population of this small matrix was that coefficient C1 gains from itself as I over h bar delta over 2. Coefficient C2 gains from itself as minus I over h bar delta over 2. And there are cross excitations with Rabi frequency, so minus I over 2 Rabi frequency minus I over 2 Rabi frequency. So our first set of linear differential equations can be interpreted as time derivative of the vector of state. Typically, we use cat vector, but we can use algebraic notation to highlight that it is vector minus I H bar, Hamiltonian matrix acting on the same vector of state. And I believe everyone would agree with this notation. So it is Hamiltonian space. Hamiltonian space. The equation that you have just derived collectively here in class has very similar shape, right? It's a set of linear differential equations of the first order, and it basically describes the same system. It's just different representation. So we can say that is d dt of density matrix written as a vector. We know that it is matrix, but we just save it. We store it in the memory of computer as a column vector. And then it is propagates in time according to Liouville superoperator. And then row here. So here we had Hamiltonian operator, and here we do Liouville superoperator. So there is a confusion with what physicists use for Lagrangian, but here in this context, it is Liouvillean superoperator. Too many vowels. View superoperator. Superoperator. So you do see, just practically observing the exercise of today's meeting, that quantum mechanics, not only of two-level system, it can be generalized, can be completely recast, completely expressed in this Liouvillean space. If we plan to focus only on a single isolated quantum system, then it is useless. It is just adds more problems. So we need, if our size of the state vector is n, then size of this density matrix in the vector notation is n squared. So we are wasting a lot of arrays and a lot of computational power. But recasting quantum mechanics in the Liouvillean space does have benefits in several situations. So it has benefits. From the top of the head, I would mention three. When one needs to explore average over ensemble of the same, of a very similar objects. So if we add them together, this average over ensemble is much easier and much more natural to do in the Liouvillean space. First thing. Second thing, if the system, if the model is being perturbed, is experiencing external optical perturbation, especially perturbations in the non-continuous, but in the way of pulses. So if the system undergoes sequence of pulses, Liouvillean representation is much healthier and much more comfortable. And the third and most important one, that the quantum system that is being placed on a hot plate is interfacing solvent, substrate, black body radiation in a thermal state, cannot be treated in the Hamiltonian space. So in order to bring in statistical averaging and interaction with ensemble, with a heat bath, with a black body, and bring system in a thermal state, one has to convert all considerations into Liouvillean space. Okay, so we have done one of our main purposes, which was the introduction of this Liouvillean space and equation of motion of density matrix for two-level system under resonant or near resonant photoexcitation. I'm going to speak a little bit more in the, and my justification to be a little more intense is that in previous years this dynamical part took a little more than half semester, and now I'm trying to squeeze material into less lectures, basically doing like 4 or 5 lectures in 3. So we need to go a little bit further, and you will not regret. I will just give some very basic considerations that will create a little leap towards our next meeting. So I'm going to return to the equations that you have derived. So from matrix notation back to this linear notation. And I'm going to analyze these equations without solving them in the following fashion. I'm going to practice adding, to add and subtract equations from each other. Add and subtract these equations from each other. So basically, I'm going to add and subtract populations and add and subtract coherences. Why I'm inviting everyone to follow it and why this exercises is planned to be completed so emergently, why I cannot wait until after the weekend. Today on last night lab and today we have introduced Bloch sphere analysis of the evolution of two-level system as a little traveler on the surface of a globe. By adding and subtracting elements of density matrix, I hope to arrive to equations intentionally designed only for Sx, Sy, and Sz projections. So before we had solution for Schrödinger equation and we plugged it into the sandwich for each of the operators. Now I'm going to dare to design a set of equations that would literally describe motion of this Bloch vector on the surface of Bloch sphere. And before starting calculations, I claim that just adding and subtracting the equations of motion for individual elements of density matrix, one would arrive to this goal. So let me start maybe from the first one. I will rewrite this row 1 with dot as minus maybe frequency and then I need to do something with imaginary unit and factor 2. So I do have row 1, 2 minus row 2, 1 divide by 2i. So I just cannot wait and keep an intrigue. If you look, how did we got this row 1, 2, and row 2, 1? We will immediately see that it is very much similar to the way how we express operator expectation value of sy as function of C1 star C2, C2 C2 without star. So second equation, row 2, 2 with dot equals to Rabi frequency with plus sign, and then it equals to the same thing, row 1, 2 minus row 2, 1 divided by 2i. So if we would add together these two equations, we would get 0, right? The right side would subtract each other. So row 1, 1 dot plus row 2, 2 dot equals 0. So if you would solve this equation, it means that well, I do not need to solve. I can just write that it is change of the population of the ground state equals to the negative of the change of population of the excited state. So they are changing in the correlated coherent fashion. Now, if I want to subtract these two equations, so row 2, 2 with dot minus row 1, 1 with dot. So it will be 2 omega Rabi row 1, 1 row 1, 2 minus row 2, 2 row 2, 1 divided by 2i. So what I can imagine immediately see, the left side can be expressed as ddt as time derivative of the subtraction of row 2, 2 minus row 1, 1, right? And if I divide and multiply it by 2, and remember 2 minus 2, 1, that those are C2 absolute value squared minus C1 absolute value squared over 2. We can interpret it as we defined at the beginning of this meeting as expectation value of SZ, population inversion. So 2 ddt of SZ is equal to omega r. And if we carefully look onto definition of this subtraction divided by I, we would see that it is related to the operator sy. I just do not want to miss factors and want to revisit it in maybe a minute and make sure that factors are placed correctly. So change in time of the SZ projection does depend on the SY projection, and it comes from just adding together elements of density matrix. Now, let's practice I believe it is correct. I believe it is correct. Factors 2 will cancel, and it will be just as Z depends on Rabi frequency as Y. So now let's practice the second strand to add and subtract other pair of equations. So the one for row 1, 2 and row 2, 1. So row 1, 2 this dot plus row 1 dot, and then I'm just looking of what is going on here. So it will be plus I over H bar delta row 1, 2. Then minus row 2, 1. So I processed the first term. Then for the rest, we can check that here we have row 1, 1 minus row 2, 2, and here we have row 2, 2 minus row 1, here and there. So they will cancel each other. One equation. So and another one, if you subtract row 1, 2 unit minus row 2, 1 period. So we will have I over H bar delta row 1, 2, and here we had a minus sign, but we have another minus from here, so it will be plus row 2, 1, and in addition, here we would have plus I Rabi frequency. I'm finishing. I know that we are over time, and I'm just completing the thought. And then we do have row 1, 1 minus row 2, 2 minus row 2, 2 minus row 1, 1. So it will be double factor. We put minus sign here, row 2 minus row 1. So since we are about to expire time, I will write the answer without working on details and factors, which will be my homework before we meet on Tuesday. But from the first equation, one can treat it summation of these two coherences as the expectation value of Sx. Because if you look onto definition, it will be C1 star C2, C2 star C1 added together, divided by 2. So, and subtraction is imaginary factor will be the definition of Sy. So minus and imaginary unit disappear when we convert this subtraction of coherences into definition of Sy. From this element, we'll get that, so time derivative of Sy will be equal to this element will give us Sx. The delta plus delta over h bar Sx minus omega rabi of Sz. So I need to double check the factors, but then we do have 3 equations. ddt Sz is omega rabi Sy. ddt Sx is minus Sy. ddt Sy is Sx minus Sz. So this set of equations controls motion of the quantum state of driven two-level system on a surface of a Bloch sphere. The first thing that we will do when we meet on Tuesday, we will prove, based on this set of equations, that S squared, that the length of this vector is constant, so that time derivative of length of the Bloch vector is 0, and it can be proved based on this equation. There are 2 limits. One limit, there is no Rabi frequencies and is 0, and we have only detuning. That would correspond to rotations in the XY plane. And another limit is when detuning is 0 and we have only Rabi oscillations. And then it will be rotations in the plane Y and Z. And if both effects are present, it is more complicated spiral motion that cannot be projected on one or another circle. I think it is more than enough for one meeting. Thank you so much for coming at all and for staying over time. Let me stop sharing. announce that the adjourn. So the meeting is done.